Hey, hello everybody. Hey, this is going to be week 6, lecture 3, and this is more applications of Newton's second law and circular motion. And so just a bit of a preview if you've not seen the week 6 lecture 2. Okay, we ended up kind of talking about centripetal acceleration and centripetal force, which we kind of put together. So today's first example on that is going to be similar to the question of the day on 1118. So if you looked at question of the day 1118 and you struggled, then you're going to use this as an example on how to do that. And then depending on how much time we have, we might go to another example, which would be non-uniform circular motion or non-uniform forces. Okay, so a classic problem in physics is a car rounding a curve, and for our purposes, it's going to be without friction. Okay, now if you guys have ever, and I'm going to be probably starting to talk with the students out there. This is Wednesday and second period, so I'm going to be talking more to there. But in a more extreme example, if you've ever driven your car or been in a car, usually on a mountain road, you will see that when you come up to a curve, okay, there'll be like, a 40-mile-an-hour curve or a 25-mile-an-hour curve. It's basically saying, hey, don't go too fast, because if you go too fast, you could run yourself off of the road. And I remember being a kid myself and thinking, 40 miles an hour, I could do this at 80 miles an hour, okay? And being afflicted with testosterone poisoning, I probably tried it, okay, and got to go faster than the posted warning sign. Now that warning sign is really there so that you could negotiate that curve without friction. So think of this curve as being, you're in a car and you want to go around this curve and it's ice, okay? So I'm going to kind of draw this from behind. So if we're drawing this behind, these are kind of the wheels, and then we're going to have this car here. Here's the back window. Here's our license plate. I heart physics. Okay, so we're going to call this angle, we're going to call that angle theta. Okay, and if we kind of think about it, and now it's kind of more, think of this as a more oblique, drawing here. Think of this curve that's going on like that. So we're going to get just kind of that direct slice here, but then it's going to kind of curve that way. And the diagram that I used in the question of the day gives a better perspective on that. And it also kind of gives you some hints. It gives you some hints with what the free body diagram is going to look like. Okay, so now, as with all of this, we want, when we're analyzing the forces, it is often very useful to draw a free body diagram, which is what we're about to do, okay? And we're going to use the dots right here. Now, because this is a little more confusing, I'm going to draw it here and I'm going to draw it here, okay? So you can kind of see the difference. Okay, so we want everything that touches it plus gravity plus friction. Everything that touches it plus gravity plus friction. Now, we already said that this is going to be frictionless, okay? So what is touching the car?
Gravity.
The road is touching it, plus we have gravity, which is going down. Okay, so now the road, as we already know, is going to be a normal force, and it's going to be perpendicular. It's going to be perpendicular to the road. And then we are also going to have the force of gravity. Okay, now, in the first thing to think about in a free body diagram is what is our convenient XY coordinate system, Now, it's a bit hard. It's a bit hard to think about this in this sense, but essentially, we're going to have one big horizontal plane. Okay, so we're going to say that this is our X direction, and this is our Y direction. Okay, so it's our normal XY coordinate system. Now, if we have this sort of tilted, and so now we've got a circle like this, it becomes a lot more complicated. And if we have time, I'm going to touch on that when we get to the next new example, which will be a question of the day for tomorrow. Okay, all right. So now if I'm going to draw this down here, I'm simply going to have this, which is my force normal, and I'm going to have here, which is my force of gravity. Now, if you've seen week 6, lecture 2, this free body diagram is the same free body diagram as if you have something like going like this. It's the same free body diagram, except instead of the rope or the tension here, it's going to be the normal force. Okay, so after we have drawn our free body diagram, we're going to go to step 4, and we are going to resolve our vectors. We're going to resolve our vectors into our XY coordinate system. So we can see that the f of g is already in that, but the force normal is not. So we're going to change this one into the y and the x. We're changing that to the y and the x. Okay, now let's think about what that angle is. Okay, so if this angle right here is theta, then this angle right here is theta, and this angle right here is phi, and then this angle right here would be theta. Okay, so now when you first look at it, at least in my eyes, this theta and this theta are the same. But, and again, in my eyes, it doesn't seem, is that right? You know, that sort of thing, because this doesn't look like it's that corresponding one, but it is. Okay, so we will get rid of this now. Let's just put some numbers in here, and we can kind of say, so let's say that our radius is equal to 100 meters. And let's say our angle is, I don't know, 25 degrees. Okay, so a radius of 100 and an angle of 25. So the question is really going to be, how fast can you go around this curve to negotiate the curve, okay, without slipping off the top of the road or off the bottom of the road, okay? So if we're going around here and we're going too fast, then, okay, the car is going to essentially creep up the bank, and if it was going too fast, it would go off, okay? But also, if we're going too slow, okay, then it would start to creep towards the bottom, okay? And if you've ever ridden a bike or ran or in a car, okay, and if you're going too fast around a curve, even if it's banked, you're going to feel yourself kind of cruising to the high end. If you're going too slow, that you would kind of go towards the middle. I'm thinking about my cross country days back in high school when we had a great course at my high school. It was all kind of in the mountains. There was like no road, but anyway, there was one thing where it was kind of this curved thing, and it was a great place to pass, right? because you'd really speed up and then you'd kind of go up on this little bank curve and then you go right around a person, which for some reason that was really fun to pass someone that way. Okay, so so now this one over here. Okay, now this is the hypotenuse and this is the angle. So now we can identify what this is, and that's going to be force normal cosine theta. And so this other one is going to be force normal sine theta. Force normal sine theta. And we can see here that the sum of the forces in the y direction, the sum of the forces in the y direction is equal to 0. Okay, now it's 0, even though it's moving, remember it's moving in this big horizontal plane, right? So it's not moving up or moving down, so it's keeping there. So in the y direction, it's not accelerating. Therefore, it's 0, and we're going to have Fn cosine theta minus f of g. Now remember, f of g is just mg. So if we rearrange this, we can say force normal is equal to mg over cosine theta. Okay, so I brought this negative to the other side, makes it positive, changed it to mg, and then divided by cosine theta, and now we're going to have a force normal. Okay, now I am preparing essentially to do a substitution, which I kind of shown you there. And now I'm going to get back to this one, but I'm going to go kind of over here. Now we're going to take the sum of the forces. But now I am not saying the sum of the forces in the x. I am saying the sum of the forces towards the center. Now it's still this sum of the forces to the center. It's all going to be horizontal. But if we're over here in this part of the curve, right, and I am going this way, my x would be here, okay, going towards the middle. But now if I'm over here on that same circle, now my x would be there and they would be the opposite sign. Okay, so what I'm really saying is I'm not strictly saying x because that implies a plus or minus, so I'm saying towards the center. And everything in this case is going to be positive towards the center. Now we can make everything negative towards the center too, but we know that whatever it is going to make it go towards the center. Now, this is equal to ma. Sum of the force is equal to ma. But as we've seen here, that AC is equal to mv squared over r. Okay, so the sum of the forces towards the center is mv squared over r. And we're going to go back to our free body diagram. And the only thing that is going towards the center is our portion of the normal force that's going towards the center, which is Fn sine theta. So we're going to have Fn sine theta is equal to mv squared over r. We'll plug in our numbers here in a second here, but we know our radius, we don't know our mass, we know our angle, we don't know our velocity. Now, you might not remember because I didn't write it up there, but my original question is how fast can we go around this curve? How fast can we go around this curve? So I want this, okay? I know radius, I know theta, but I don't know my normal force. Okay, and that is where we're going to go back to this one, and now we're going to substitute force normal is going to be mg over cosine theta. So mg over cosine theta. That's my substitution. Sine theta is equal to mv squared over r. Now, even though if we've got a heavier, a more massive car, there's going to be a greater normal force than if we have a lighter car. But it really doesn't matter. It really doesn't matter what mass we have because the mass is going to cancel each other out. Okay? And then one other thing that we have here, we can see that we have sine over cosine. Which, as all of you know, is tangent. So we can have tangent theta. Okay, tangent theta is equal to v squared over r. Tangent theta is equal to v squared over r. Now, if I knew the velocity and the radius, I could solve for the angle. If I knew the angle and the velocity, I could solve for radius. Okay, but in this case, I'm asking for the velocity. Okay, so we're just going to kind of put these up here so we can see it a little bit better. And so now we can say tangent theta r square root is equal to our velocity. Okay. All right. So now in our questions with numbers, we're going to say the tangent of 25 degrees times 100. And then we're going to take the square root of that. Okay, so and I'm getting 6.8. So velocity is equal to 6.8 meters per second. Okay. Now, you guys, that's only about 15 miles per hour. 15 miles per hour. Okay. So 25 degrees doesn't seem like a lot, but if you saw a 25 degree angle in a car, it would seem pretty extreme. All right. So again, on your question of the day for November 18th, okay, there is a question about this, and it's really going to ask you three things. It's going to set up a situation of how fast you can go at a certain angle and a certain radius, okay? And then it's going to change, and it'll end up asking you what the angle is at a particular velocity and radius, and then it'll ask you what the angle has to be to go to speed if the radius changes.
What question of the day is going to have that?
This is this is an example of a question of the day for November 18th. So again, if you look specifically at essentially the free body diagram and really the equations, the question of the day from yesterday, okay, which had to do with a mass on the end of a string going in a circle, okay, a lot of the math looks exactly the same, okay? All right, so now we're going to do essentially a quick one here that is going to deal with going around in a circle, but on a flat curve, okay? So I'm going to erase this, and we're going to see how different it is and how similar it is. All right, so now we're going to have a flat curve, okay? Here is our same, we're going to make this now a truck. And we're going to put a box at the end of the truck. So here is the cab. of the truck. Okay, so again, we're going to end up kind of going around this road like this. And now we're going to have between the crate and the bottom of the truck, we're going to say we're going to have a coefficient of static friction that is equal to 0.6. Okay, so the coefficient of friction between the crate and the bottom of the truck is 0.6. And we're going to essentially give it the same 100-meter radius. And we are now going to say, how fast can we go around this curve before the crate starts to slip? Before the crate starts to slip. And if you've ever been in the back of a pickup, when you go around a corner, you can know that you're getting thrown, or even the back of the seat, in the back of a car, if you go too fast, you're going to feel that sensation of being thrown to the outside, okay? Now, we're going to draw a free body diagram. Now, we're really going to concentrate on just this crate here, okay? But we're going to have the force of gravity going down, and we're going to have the force normal going up. Well, if we have the normal force and the force of gravity, they're only in the y. So what is making the crate go towards the center? What's making the crate go towards the center?
Is this frictionless?
It's the frictional force. Okay, so we're going to have this force of friction that's pushing us to the middle. Now, if we drop down, and look at the tires, what is making the car go around in a circle? What's making the car go around in the circle? And for a flat curve, it is the friction. It is the friction between the tires and the road. Okay. Now, this is kind of interesting, maybe a little counterintuitive. It is not, it's not kinetic friction that's keeping the tires, making it go towards the center. Now, even though the tires are rotating this way, okay, any motion that would cause it to slip would be this way. So you can have a tire that is rotating, okay, but when we think about it from the different view, okay, so even though it might be rotating this way, there is no movement. There's no movement left or right unless you start to slip, okay? So that would be static friction. All right. So now we have everything that touches it, friction, or everything that touches it, normal force, plus gravity, plus friction. And now we're really doing the same thing. We're going to say the sum of the forces in the y is equal to 0. It's not going to move up and down. So that's going to be force normal minus mg is equal to 0. So again, mg and force of gravity are the same thing. So now we can say force normal is equal to mg. Force normal is equal to mg. And now we are going to do the sum of the forces towards the center, okay? And that is going to equal to mv squared over r. Okay, again, the only thing that making it go towards the center is the force of friction. And we know that force of friction is mu force normal. So mu force normal is equal to mv squared over r. And we know our normal force is mg. So we can say mu mg is equal to mv squared over r. And again, our masses cancel out. Our masses cancel out. So if we're looking for velocity, that's going to be the square root of r mu g. R mu g. Which kind of looks like rug. The square root of rug. All right. So if we wanted to do this example, now we can say the square root of 100 times 0.6 times 9.8. So 100 times 0.6 times 9.8, and that's going to be 24 meters per second. All right. You guys, I am going to show you what the free body diagram looks like if we add friction. If we add friction to a banked curve. Okay. So again, if we have our banked curve and we've got our car here. What are all the forces? Okay, now we want everything that touches it. So what's going to touch it? And again, this is obviously looks extreme here, but we're going to have the force normal, and we're going to have mg. Okay, it looks pretty simple so far. But now the force of friction is going to be down the ramp. Down the ramp if we're going too fast. But it's going to be up the ramp if we're going too slow. It's going to be up the ramp if we're going too slow. So here's the issue here. Remember, the sum of the forces in the y would still equal 0. So we would have force normal cosine theta. Okay, force normal cosine theta minus mg minus the force of friction, which is mu force normal sine theta. So this would be mu force normal sine theta, and that would equal 0. Okay, and if we really think about it, we could say plus or minus there. We could say plus or minus there. Again, I'm only drawing it as if we're going too fast. Okay, and now if we now say the sum of the forces towards the center is equal to mv squared over r. And now what we have going towards the center is force normal sine theta plus the force of friction cosine theta is equal to mv squared over r. And this force normal sine theta plus mu mg cosine theta is equal to mv squared over r. And if you guys remember what we did last time, okay, in this similar sort of question, is we substituted for the normal force, okay? Well, by substituting for the normal force, this gets a little bit more gnarly. So we can say force normal cosine theta minus mu force normal sine theta is equal to mg. then we can factor out a normal force and say cosine theta minus mu sine theta is equal to mg. And then we're going to divide by the normal force, which is cosine theta minus mu sine theta. That's going to get rid of that. And now we would substitute this where we have force normal, okay, which would be in there. And then we can see we got a lot of gnarliness to it. Yeah.
Nathan, I can't really see anything.
What's that?
We can't really see anything you wrote right
You cannot see through this?
now.
Let me. It is not. It is not a huge. It is not of a huge material concern because we. I'm kind of showing you there where what looks like a very simple addition, to a problem by just adding friction to a curved surface, we're going to end up with a rather complicated, we're looking at a rather complicated sort of equation. Okay, and so it can get kind of nasty pretty fast. All right, so that kind of covers those cars going around a curve, but again, it's sort of similar. All right, now we're going to shift our gears here and kind of finish off, not with the horizontal curve like I was showing you before, but what is called a vertical curve. Okay, so if I take this mass on the end of a string, but now I'm going in a circle. Let's say that I'm really good and I can swing this at a constant velocity. If I can swing this around with a constant velocity, okay, then what is the tension? What is the tension in the rope? Well, if it is going at a constant velocity, and really what I should say here is a constant speed, because since it's going in a circle, it is changing velocity at every instant, right? But it's keeping a uniform speed, okay? And as it goes here, so we can say at any one instant, we can say the velocity because that velocity is tangent, okay? But technically, when you take the whole circle, it's going to be velocity. All right, so I'm going to erase, even though I'm going to end up putting this back in here, we're just going to erase it to get a circle. So now, if we have a mass on the end of a string, okay, and it's going in a circle, okay, so essentially everything is going towards the center of the circle, right? So now we can say that the sum of the forces towards the center is equal to mv squared over r. But right here, and we'll call this at point A, what is touching? What is touching that mass? Force of gravity is going to be on there. We're ignoring friction because there's no two surfaces. There's no two surfaces that are touching. Is there air resistance? Yes. Are we ignoring that? Yes. Okay. And so the obvious thing here is the rope is touching it. Now, I'm going to call that tension. Okay. And for some reason, I just like calling it T, which plenty of physics books do that. Okay. Other physics books will say force of tension like that. And most of the time, I will do the force with the subscript there. So, for example, if we have normal force, okay, there are other physics books will just call that normal force with an N, right? So I'm not actually that consistent there. And the problem, even though I still do it, the problem with this T is that it can be confused with the period, which is the time it takes for one revolution. So very often you're going to end up, you could end up with a T meaning tension or a T meaning period. And they are different enough aspects of the same, what could be the same problem, that you can distinguish them. All right, so tension is touching it, and that is going to make it go towards the center. Okay, what else is making it go towards the center? As someone already said, we already have the force of gravity. Okay, so we're going to have tension plus mg is equal to mv squared over r. So if we're going to solve for tension, we're going to have mv squared over r plus mg, which we could factor out an m and say v squared over r plus g. And that would be the tension. That would be the tension at the top. Actually, this would be minus, because it was on the left and I moved it to the right. So it would be minus. Now, let's look at the same thing. Let's look at the same thing when we are at the bottom. When we're at the bottom, we're still going to have tension. We're still going to have tension that's going up. Okay? But gravity is now going down, right? So we're again going to have the sum of the forces is equal to mv squared over r. And that's going to be tension minus mg is equal to mv squared over r. And now when I bring this negative mg to the other side, it is going to turn positive. And we're going to end up with tension is equal to m times the quantity of v squared over r plus g, where the tension at the top was minus g. And I want you guys to think about, as you are going around like so, you can probably feel what that tension is changing. Okay, now I am going to ask you in tomorrow's question of the day, what would it be like if we're essentially right here or horizontal? Okay, and that's just going to, when it's not vertical or horizontal, you're going to end up with some sines and tangents, or sines and cosines. But if I'm going around like this and I slow down, okay, we can see that it no longer goes in a circle. We're going to get to a certain point here where the rope goes slack. The rope goes slack. So what is that minimum velocity? What is that minimum velocity that we can go and still make it around in a circle? Okay. So we're going to go to, and we're going to talk about the tension. We're going to talk about the tension at the top here. And so we're going to say tension is equal to the mass times v squared over r minus g. Okay? And that is equal to tension. And actually, we're going to do the same thing, except we're going to say, we're going to start up here. We're going to say tension plus mg is equal to mv squared over r. And you'll see why I rewrote that. Okay? All right, so as we're going around in a circle, okay, and you can kind of see this, as I slow down at a certain point, the rope goes slack. If the rope goes slack, what's the tension in it? It's going to be 0, okay? So essentially, at the minimum, T is equal to 0. Therefore, mg is equal to mv squared over r. M's cancel out. So v minimum is going to equal to the square root of gr. So the minimum velocity that you have when you're going on the inside of a circle is the square root of gr. Because now only gravity is making it go towards the center, because the tension goes to nothing. All right, now here's the last bit here. As you go over the top of a curve, not on the inside of a curve, everything changes. Okay, and if you've ever, I'm sure you've done this on your bike. When I was a little kid, that was the beginning of the BMX craze. Okay, and every kid wanted, well, when I was a kid, there was no such thing as a BMX. Okay, but we had all of these bikes that turned into BMX because we would go to some field, dig a ramp, and jump our bikes over the ramp. Okay. Subsequently, we broke a lot of bikes. Okay, and therefore people started designing bikes just for that case. Now, when you're going over, okay, what is the maximum velocity? What is the maximum velocity that you can go? Okay, that's going to be on tomorrow's question of the day as well. And you're going to set it up in the same way. All right, we'll see you guys next time.